of Materials and Metallurgy, National Institute of Technology, Trichy. So today's lecture, it is like so particular about what are the different biomaterials and how to select the biomaterials and on what basis these metallurgical concerns are there. So all these things we'll be covering. Okay. The fundamental insights on the present techniques to fabricate different biomaterials and what should be the selection criteria for choosing a biomaterial. All these things will be addressed. Okay. So first let me brief about like what is a biomaterial and what are the qualities that are required if it is so-called to be a biomaterial. So if the material should be biocompatible, like if a material is so-called as then it should promote a bionic function. Bionic function in the sense it should not be like toxic to the human cells. Okay, so that is so called as bionic function. Then secondarily, it should be like tissue friendly in nature. The tissue friendly in nature is nothing like, for example, if you are considering two implant materials. So one is like stainless steel 316L implant, which is most popular, and another one is like titanium material. Okay, so these two materials are very biocompatible. There is no doubt in that. But when we are considering this titanium implant, it is like more tissue friendly. If once the implant is fixed in our body, then automatically tissues will start growing over the implant. Okay, so that is so called as tissue friendly in nature. Okay, then the third one is like it should support the osseointegration property. So osseointegration property is nothing like a bone integration property. The bone, it should integrate very easily. Like for example, if a person has undergone fracture, then his bone should minimum ample of time. It should not take a prolonged time. Okay, so your implant should be in such a way that it should promote your bone joining ability. Then the next one is antibacterial in nature. Okay, antibacterial nature in the sense, for example, if a biomedical implant it is implanted in the body, then of course it will be like it will be biocompatible in nature. But however, there is no guarantee that the material will be like antibacterial. Okay, antibacterial in the sense, for example, if an implant is implanted in the body, then automatically some kind of bacteria such as Escherichia coli, which is so-called as E. coli bacteria, or else Streptococcus aureus. So that is also one of the most common bacteria. So even such kind of bacteria could adhere over the implant surface, and later it will cause a lot of pathophysiological problems. So we are like so concerned about the antibacterial nature of a implant. Okay, so an implant, it should not be like a completely biocompatible. It could be completely biocompatible, but in the same way, it should be antibacterial in nature. Okay. Then the next one is a corrosion and wear resistance. Okay. So obviously, now when an implant is fixed in a body, then automatically this implant will be like be having a consistent interaction with the blood and also some kind of body fluids. So which will cause some kind of like an etching effect, and it will start slowly corroding your implant material. Say for an example, magnesium implant. Okay, so magnesium is a well-known material which is more biocompatible, but especially it has a very poor corrosion resistance. So that's why a lot of ingredients like reinforcements were added with magnesium to improve the corrosion resistant properties. Okay, so that the degradation ability will be like will be increased, like the degradation resistance could be increased. Okay, so then another one is the wear resistance. Say for an example, if now if some femur bones or some kind of prosthetics, it will have like a rubbing action. Okay, like one implant material will be like rubbing with the other material, so which will lead to like a releasing of some micro debris. So your material, your implant material, it should be like more wear resistant material. So then the other things is like it should not release any neurotoxic substances at the time of degradation. The neurotoxic substances in the sense, for example, you can take stainless steel 316L. In stainless steel 316L, minimum like nickel content will be like up to like 10 to 12% of nickel content will be there, like minimum 8 to 12. So when a material is getting corroded, then nickel will be like it will mix with the blood. Okay, the metal will release some nickel content in the blood, and that nickel content will lead to a lot of allergic reactions in our body. So your implant material should not release such kind of like allergic materials. Okay, so it should be that much corrosion resistant. Yes. So that is very, very important. Then the last one is like it should promote the cell adhesion and cell growth. Okay. So generally, when an implant is fitted in your body, then of course now that implant it should create a conducive environment for the cell adhesion, and it should help the cells to proliferate over the implant. Okay. So which is otherwise called as cell growth. Okay. So let's step into the next slide. Now I have classified what are the basic biomaterials which has been used in this recent era. So this biomaterials, it was like broadly diversified into like metals, polymers, ceramics, and composites. Okay, metals in the sense we used to use like stainless steel 316 or titanium or niobium. So even such kind of materials that has been widely used, and even some polymers also that has been used. This polymethyl methacrylate, polyester urethane, likewise some different biocompatible materials that has been used. Then ceramic materials like cerium. Okay, cerium is one of the well-known ceramic which is highly biocompatible, and also it is having antibacterial ability. Okay, so even such kind of materials has been used. This titanium nitride, it is one of the most spectacular material which has been used in wide range of applications, especially in prosthetics. Okay, so it has been added with pure stainless steel. It has been this titanium nitride has been added with pure magnesium and this pure titanium. It has been added with n number of materials to form a material more corrosion resistant and also wear resistant. Even we could observe some kind of composite materials as well. This titanium is developed a new alloy. As this it will improve the corrosion and wear resistance of stainless steel 3160. So that's why this kind of titanium nitride kind of ceramics, it could be added with some composites. Okay. So even niobium, it could be added with titanium 6 aluminum 4V alloy. Okay. Even cerium could be doped with magnesium alloy. So yeah, there are some aspect ratios of mixing this kind of biomaterials. Okay. So there are many biomaterials out there, but before choosing any biomaterial, so we should have certain criteria in our mind that it should satisfy all these criteria for fulfilling the biomedical implant production. Okay, so based on those criteria only we'll be choosing this kind of biomaterials. First, let's go. I mean, before stepping into further, let me classify like what is the difference between an alloy and a composite, because many people were like quite getting confused, like what is alloy and a composite. So alloy in the sense you can mix n number of materials, but at least one should be a metal. So which is nothing but an alloy. That means you can mix n number of materials, at least one should be a metal. And whereas a composite, you can mix n number of materials, and there is no necessity that at least one should be a metal. Even all can be metals, or all can be non-metals, or it can be a mixture of metals and non-metals. So even it could be ceramics, even it could be mixed with a metal. Okay. So for composite, now you can mix in any forms. Okay. But whereas in alloy, you have to mix each and every material at its own melting point. For example, the melting point of like magnesium will be different. For example, if you are adding titanium nitride with magnesium, then obviously the melting points will be like different. So magnesium should be melted separately to its own melting point, and titanium nitride, it should be melted to its own melting point. When those two liquids are like highly saturated liquid, that will be mixed together in a liquid state to develop a new alloy. Okay, so alloy means each and every material should be melted to its own melting point. Okay, to form alloy. For example, in composite, say for an example, aluminum metal matrix composite. Okay, so in aluminum metal matrix composite, the name itself indicates that aluminum is the main matrix material. So will be melted to its melting point, and other reinforcements like a titanium nitride, if you're adding some small quantity of like nickel or titanium, then it will be like simply preheated like 300 to 450 degrees C, and it will be added to form a composite. So only the base material only is going to get melted in composite, and the other reinforcement material whichever we are going to add, that will be like simply preheated to develop a composite. Okay, so right now I hope that you people would have clarified that what is the difference between a common difference between an alloy and a composite. Okay, so in alloy, each and every individual material should be melted to its melting point. Okay, so in alloy, it would be mechanical, metallurgical bonding will be taken place. But whereas if you are considering a composite, only a mechanical bonding will be taking place. There is a difference between a metallurgical bonding and a mechanical bonding. Okay, so in metallurgical bonding, some kind of chemical reaction would be taking place, because each and every individual material will be melted to its melting point. So in alloy, there is a metallurgical bonding. In composite, there will be a mechanical bonding. Okay. So let me quickly step into the slides. So before choosing any biomaterial, so first of all, we should be concerned about the corrosion resistance of a material. Okay, so now we can see here a tooth implant. Okay, so this implant is made of stainless steel 316L. For example, now when people they undergo like this tooth removal, then automatically there's an implant rehabilitation. It is a most common technique. So we could observe that a titanium implant is drilled inside our teeth, and it was fitted over there. And this titanium implant, it will be in consistent interaction with your saliva. Okay, so this saliva, it will be like acting like an electrolyte. Okay, so this saliva electrolyte, it will start etching your titanium, and it will start forming some kind of corrosion products, which you could observe in that figure. Some brown color, some corrosion products that could be noticed. Okay, so this corrosion product, it will be like interacting with your soft tissues in your teeth, and which will eventually, it will cause a lot of irritation problems. Okay, so we could see some kind of inflammation, especially in the implant zone. In the implant zone, we can see some kind of like some small swellings that are more visible. So you are leaving this swelling as it is, and if you are letting this corrosion to occur, then the last stage will be like it is like near to the cancerous stage. Okay, so yeah, unhealed wound will turn more cancerous. Okay, if a wound is there and if it is not getting healed for a long period of time, then eventually it may cause like cancer. Okay, so that is the most important thing that which we should be knowing, is if an implant was fitted in our body, it has its own duration. Like say for an example, stainless steel 316L means maximum you can use that implant for 10 years. For example, if it is titanium, you can leave the implant in our body for 20 years. So after that, this implant should be replaced with a new one, or else this kind of corrosion may happen eventually, and it will cause a lot of pathophysiological problems. Okay, so not only this dental implant, even in hip prosthetics, or else even in orthodontic application, or else even prosto application. So whatever the application, we might be using some biomaterials, its own durability. Okay, so now we could see that what are the different orthopedic implants here. Okay, so some orthopedic implants, we can observe that this particular material is like a magnesium material. So this magnesium material, it has undergone some kind of corrosion due to the consistent interaction with the blood. Okay, so the corrosion, it could be of any type. So the corrosion, it was broadly diversified into many types that we will be covering in the upcoming slides. But this kind of corrosion products that will mix with the blood, and it will lead to septic shock. Okay, so it is the most common problem, and it will cause sudden fatigue failure. In mechanical terms, we will be discussing what is a fatigue failure. It is like unexpected failure due to the repetitive loads. Okay, so the this kind of fatigue failure that could be possible. So in order to avoid that, our material should be having sufficient fatigue resistance, and also it should have enough corrosion resistance properties as well. Okay, so if a corrosion that happens due to like a rubbing of one implant over the other, so such kind of corrosion is called as fretting type of corrosion. Corrosion, it could be of many types. We will be covering in the upcoming slides. But now when two implant materials that will rub with each other, so at that time, if any corrosion that happens, that is called as fretting type of corrosion, which we could observe here. And here I have given some couple of examples like how an implant that will exactly look. Okay, so if it is getting corroded, then in what way it will be looking? The appearance was shown there. Okay, so let me quickly step into the next slide. So this kind of an implant, okay, this kind of implant, it will undergo a common type of corrosion. It is called pitting corrosion. Okay, this pitting corrosion, it is the most common corrosion problem, especially with stainless steel and titanium implants. Okay, so especially some small micro pits that will be developed in the surfaces of the implant, and when it is due to the etching effect. Okay, so now whenever our body fluids are like interacting with the implant surface, then it will start etching our implant, which will lead to this kind of like small pit formation. Okay, some small micro pits, and it's a SEM like scanning electron microscopy images were shown here. So generally, when we are like looking in our naked eye, we could not observe small micropits and all. But whereas when we are looking in a SEM microscopy, then of course we could observe some small micropits and each and everything, like small pits, pock marks, some recast adhered degrees, each and everything that could be observed when we are observing in scanning electron microscopy, which is nothing like SEM morphology. Okay, we can see that some small micropits were there, which was developed. I mean, during the time of like implantation. Okay, so later it will progress and it will later progress into a next level where which will be having some small rust particles that will be adhered over the surfaces of the implant. Okay, so which is commonly called pitting type of corrosion. This is the most common type of corrosion in most of the implants. Okay, so if we are biomaterial, our implant material should be having some sufficient amount of like pitting corrosion resistance. Such kind of materials only should be opted to be a biocompatible material. Okay. So here we could observe some couple of examples. So stainless steel 316L. Okay, stainless steel 316L implants that will be of like different types of implants were there. And why we particularly use this 316L? What that L indicates means L is nothing like a low carbon version. Okay, so generally the carbon content it will be like 0.03 or in that particular range. But in stainless steel 316L, particularly the carbon content is kept very low, so that the material will be like more biocompatible. And another advantageous feature with this stainless steel 316L is the chromium content. Okay, so since the chromium content it will be in the range of 16 to 18 weight percentage. So this chromium it was like a highly corrosion resistant material, as we know already. So this chromium will be like increasing the corrosion resistance of your stainless steel. So which will form a protection film, which is called passive film. Generally, we describe a corrosion resistant film is called passive film. So it will form a chromium oxide, Cr2O3 passive film. It will be formed. So that will resist against corrosion. Okay, so that is giving the high corrosion resistance for the stainless steel 316L. Okay, so if that kind of Cr film it should be formed, then obviously your chromium content it should be more than 16 weight percentage, then only Cr2O3 passive film will get formed. Okay, so we have to choose some material like which will improve the corrosion resistance. As I told you earlier, this titanium nitride, it is one of the most vital material which will improve the wear resistance and also the corrosion resistance ability of any material like magnesium, stainless steel, titanium. Like you can use titanium nitride with n number of materials. Okay, then here we could observe like how we can measure the corrosion resistance. Okay, so now we have chosen an implant and how we can measure the corrosion resistance needs. So generally we can go for like weight loss method. Like now if your implant, okay, in a beaker, the implant material was like immersed inside it. Okay, so then automatically the area which is exposed I mean exposed to simulated body fluids. Okay, so here water-like substance is there, which is called simulated body fluids. Okay, so we cannot check an implant directly to the human body because we have to get a FDA, Food and Drug Authority approval. Then only we can implement that implant in real time. So now since we are in the testing phase, we could test our implant like corrosion resistance or biocompatibility using this kind of simulated body fluids. Okay, so simulated body fluid is the one which is having like a similar constituent, whatever the things that are present in our blood, the same pH will be there. Whatever the blood constituents are there, the similarly all the constituents that were present in the simulated body fluids. So instead of checking in our human body in real time, we can check the corrosion resistance of this material using this kind of simulated body fluids. So it is there are a lot of solutions are there, like Ringer solution are there, then Kukumbu solution are there, different types of solutions are there. We can check in any types of simulated body fluids to evaluate the corrosion resistance and biocompatibility of the material. Okay, so when the implant is immersed in the simulated body fluids, then automatically the metal will start releasing some free electrons. Okay, so which could be seen in terms of bubbles. Okay, some bubbles were formed over here, so which now some kind of like electron releasing is taking place. Okay, so whenever we pour acid over any metallic surface, then automatically some kind of bubbles will be popping out from the material. So which means that the metal is releasing some kind of free electrons Okay, so those free electrons, when it is released, then obviously it will lead to small micro holes or pit formation. So which was I described as pitting corrosion. Okay, because the metal, it started releasing some small amount of free electrons, which will come in terms of bubbles. Okay, so these bubbles are called as passive film. Okay, so if the thickness of the passive film is like very high, it means that your material is like more corrosion resistant. For example, if a stainless steel implant is immersed inside a simulator body fluid, then automatically this chromium oxide layer will get formed. Where it means that the bubble, it contains chromium oxide. Okay, like because chromium is a highly corrosion resistant material, so which will be reacting with the simulated body fluids, and it will release that substances. Okay, so here we could observe some kind of couple of examples over here. I have shown schematically also as well. Let me move into upcoming slides. Okay, so previously we have observed a weight loss method. Okay, so initially, like your metal will be like losing some free electrons. Obviously, it will lead to some weight loss of your material because some oxide layers will be formed. So obviously, the weight density of your material, it will get eventually it will get reduced. So even this kind of methodology is the oldest technique which we never use at present. So another most commonly used technique at present is potentiodynamic polarization. Potentiodynamic polarization, it is a most common technique. So where we use a potentiostat. Okay, so potentiostat, it is a equipment which is used to evaluate the corrosion resistance of a material. Within 1.5 hours, within 2 hours, it could evaluate what is the corrosion resistance of your material. If we have like made an implant, okay, and if we would like to evaluate what is the corrosion resistance of that implant, means then a small implant sample would be cut in the dimension like 1 centimeter cross 1 centimeter. Okay, 1 centimeter width and 1 centimeter length. Okay, so that kind of a small square sample that could be cut, and the thickness, it could be up to like 2 mm to 3 mm thickness it could be. So which we generally use it as a working electrode. Working electrode is nothing but our implant material. Okay, so which are the implant sample material it is there, so that will be like a working electrode. And the another one is like counter electrode, and the other one is like reference electrode. These three electrodes will be there for evaluating the corrosion resistance of a material. Okay, so many people will be like puzzled how I can extrapolate the graphical values. How could I tell that this material is corrosion resistant or not, and on what basis I could tell that this material is corrosion resistant. Okay, so based on the values, how could I tell this material is corrosion resistant or not? So we will be seeing in the upcoming slide. I hope that in potentiodynamic polarization assay, we will be considering totally three electrodes. So one is the working electrode. Working electrode is the implant material. Then the next one is the reference electrode, which we generally use like a standard hydrogen electrode or a standard calomel electrode, because the electrochemical potential is already known. Okay, for hydrogen electrode, it is like 1. So obviously, the standard electrochemical potential is already known. So that's why we are using like a hydrogen electrode as a reference electrode, or else we can use like a saturated calomel electrode. And even we could use like different materials are there. We can use those electrode, but generally we can go for like standard hydrogen electrode as a reference electrode. And the other one is the counter. This counter electrode, generally we use platinum wire so that the circuit will get completed. What is the use of counter electrode means? The circuit will get completed if you are using a counter electrode. Okay, so these three electrodes, we will be evaluating like what is the corrosion resistance of the implant material which we have fabricated. Okay, so I have shown the circuit diagram over there. So this will be connecting a circuit. Then okay. So once this potentiostat is connected, I'll be generating some graphical values. Okay, so that graph is called as Tafel plots. Okay, so Tafel plot, it is the most common graph which will extrapolate what is the corrosion resistance of a material. Okay, so it will be like this potentiostat, it is like interfaced with a computer, and in computer automatically the graphical values were represented by means of a Tafel plot. Okay, I will show some couple of examples, and I will let you know that which material is corrosion resistant. We could observe on seeing the graph itself. We could come to a conclusion. Okay, so this graph was drawn between like this E, it denotes that the potential which we are applying, and I is the corrosion current. E is the corrosion potential, and I is the corrosion current, which we generally tell in terms of like a milliampere per centimeter square, because 1 centimeter square, 1 centimeter square sample is like exposed to the corrosion. Okay, so generally we will be filling the simulated body fluid as an electrolyte. Okay, so here we could observe this working reference electrode and counter electrode. All these electrodes, all these three electrodes were completely immersed inside electrolyte, which is nothing but simulated body fluids. I already told Ringer solution could be used as a simulated body fluid, or Kukumbu solution it could be used, and even few other solutions are there. In those solutions, these implant materials that will be immersed. Okay, and we will be evaluating the corrosion performance. Okay, so here we could observe this Tafel plot. So in this Tafel plot, we will be getting this E core and I core value. So these two values we will be getting. So based on these two values, we will be determining what is the corrosion resistant of a material. Okay, so we could see the upcoming graphs. So in this in the first graph, we could see that this red color graph, which is having a very high corrosion potential. Okay, so the corrosion potential is very high. Okay, as compared to the blue one. Okay, as compared to the blue one, this red color one, it is having a very high corrosion potential. So obviously this red color one, like which is like graphene, nickel, titanium, so that is more corrosion resistant as compared to the uncoated one. Uncoated one, the corrosion potential is very less. Okay, so the corrosion graph, it started declining. So it means that the maximum potential it has reached, and there are no more free electrons left to get corroded. Okay, so automatically the corrosion potential it started decreasing. So so obviously this uncoated nickel titanium, it is like less corrosion resistant as compared to the graphene nickel. Okay, graphene nickel titanium, that is more corrosion resistant. So which we could observe on seeing those graph itself. And in the second graph, we could see that like some areas where we have shown what is a passivation area. Passivation area means it is the area where small kind of pits that will get developed. So that kind of areas. Okay, so in those particular areas, some small amount of pits that will be formed. Okay, now so after that, then your passive film will become unstable. Okay, for example, I told earlier, now if a material is like getting corroded, then it will be losing a lot of free electrons, which will come in terms of bubbles. Okay, so if all the bubbles are extra were completely exhausted, then some small holes will be formed in your sample. Okay, so which is called as a passivation or a pitting. Okay, so those kind of areas that will exist when the pitting potential it is exceeding the maximum limit, then small holes will be formed. If you are applying more amount of corrosion potential and corrosion current, then more amount of like passivation, small holes will be formed, which is called as a passivation area. Then at the bottom we could observe that some kind of cathodic reactions will be taking place, anodic reactions will be taking place. Okay, so we will be like generating a graph, and graphical values like ECOR and ICOR values will be provided. Okay, so ECOR and ICOR means ECOR is nothing but the corrosion potential, ICOR is the corrosion current. Okay, so generally, if a material is if this material, if it is called to be corrosion resistant, then the ECOR value should be more higher and ICOR value should be very less. So it means that you are applying more more corrosion potential, but your material is not losing any free electrons. It is absorbing the current and it is acting like a capacitor. It is storing the charges, but it is not leaving the free electron. If it is leaving the free electron, it means that your material is getting corroded. Okay, so it means that the corrosion current will get increased if it is losing a lot of free electrons. Okay, so your material, it should act like an insulating material, or else it should act like a capacitor, so that the corrosion resistance would be rather higher. Okay, so ECOR is nothing but the corrosion potential, ICOR is nothing but the corrosion current. For if you want a material should be more corrosion resistance, then the ECOR value should be very high and ICOR value should be very less. So let's see some couple of slides as well. So here we could observe that some few graphs were there. So here we could observe that this again this red color line, it is like showing the highest corrosion resistance as compared to the black, blue, and this kind of violet colors. Okay, so among all these colors, this red one, it is having the highest corrosion potential. Okay. Then in the third figure, we could observe that this red color line, it is having a very high corrosion potential as compared to the black one. So it means that this red color graph, it indicates that that material is highly corrosion resistant as compared to the black one. Okay, so on seeing the graph, it's which material is corrosion resistant. Then secondarily, we have to go through the ECOR and ICOR values. If the ECOR value is very, very high, and if the ICOR value is very, very less, then that material is highly corrosion resistant. That's it. So obviously, wherever we do testing, definitely they will be providing the ECOR and ICOR values. First, go through the ECOR and ICOR values. So after go through that, whichever the ECOR value is very, very high, then wherever the ICOR value is very, very less, just mark it, that would be having the very high corrosion resistance. That is a simple way to evaluate which material is corrosion resistant. Okay, so here we could observe a Tafel plot. Okay, so this kind of like graphical representation of corrosion current and this corrosion potential, it is called Tafel plot. So in Tafel, now, so totally 4 different readings were there. Among all these 4 different readings, we could observe that which is having the highest ECOR value. Okay, so the highest ECOR value is like 45. Okay, this 45 degree, which was shown with the blue color, which was having a highest ECOR value, which is like minus 0.113. Okay, so for example, if you are having like a negative value, is it like a minus 5 is bigger or minus 8 is bigger? Obviously, minus 5 only it is bigger. Okay, so likewise here we are having like ECOR values like in all negative signs, which we should notice that. So among all these negative values, there's this highest ECOR value is minus 0.113. Okay, so now among all these values, which is the highest ECOR value, and whichever is the lowest ECOR value is like we could see that among all the ICOR values, this 45 degree, which was showing the least ICOR value. So this 45 degree, this blue graph only, that is like highly corrosion resistant as compared to the others. Okay, so this is how we will be evaluating the material which is corrosion resistant. For example, if we are comparing 2-3 samples, then among these 3 samples, which material is corrosion resistant? Now, which material is comparatively having high resistance to corrosion, means whichever the material is having high ECOR value, and ICOR value should be as less as possible. It means that ICOR value is less, means your material is not releasing any free electrons. Okay, so then automatically it will be acting as a capacitor. It will be observing the charges, but it will never release any free electrons to pass through. It means that your material is not getting corroded. Okay, so that's how we generally evaluate the corrosion resistance of any implant material. Okay. So if any corrosion that happens, so generally it could be like in this surface morphology only. Okay, so if a corrosion that happens, some small amount of blisters that could be like more visible, some small pits also that could be visible. So some surface and all, it will get some etching effect. So that's why this kind of blisters that were appeared over there. Okay, so these are the most common surface morphology of a corroded sample. Okay, if a sample has undergone corrosion, so maximum within the 6 figures, like most of all the materials that will come into this category only. So this is how a corrosion morphology that generally looks when we observe it through SEM morphology, like scanning electron microscopy. If we generally see the rusted area, this is how the rusted area it will appear. Okay. So I had my material. I have done corrosion testing. Then how would I know that exactly some kind of like oxidation has taken place or not? Okay. So in order to evaluate that either my material has undergone corrosion or not, I'll be measuring the corrosion resistance through this kind of like EDS mapping. Okay. So through EDS mapping, I could see that how much amount of material was, how much amount of material that has exposed to corrosion. Okay, that I could see through EDS, this color mapping. So each and every individual elements, like for example, my material is stainless steel, means obviously iron content is there, content is there, silicon content is there, potassium, likewise all material contents are there. So which was mentioned in terms of like EDS color mapping. So in this particularly oxygen mapping also was made. So this was like represented with a green color. This indicated that my material has undergone some kind of corrosion effect. Okay, so whenever our material has undergone corrosion, then obviously we could observe that either my material has undergone corrosion or not through this EDS, this energy dispersive spectroscopy. So it is the most common technique where we could observe that our material has got corroded or not. Okay, so in oxygen mapping, it has shown that some oxides were formed. So it means that got corroded. So it is a confirmation test that either your sample has undergone corrosion or not. Okay. Then upcoming slides. Okay. So in a metallurgical perspective, okay. Now how we could observe corroded morphology means. So through the SEM analysis, when we will cut a small sample like this and we will be surface morphology in the surface. So your implant material, it may be of bigger size, but it should be dimension like 1 centimeter cross 1 centimeter. That is the ideal geometry for the SEM analysis. And you could observe either samplers have undergone corrosion or not, either what are the corrosion products that were there. So even everything it could measure by means of SEM and EDS analysis. Okay. So generally this energy dispersive spectroscopy, that is the equipment which is most commonly interfaced with SEM machine itself. So if you are taking a surface morphology, for that particular surface morphology, you could evaluate either that surface morphology, what are the elements are present. You could observe through EDS mapping, EDS color mapping. So each and every individual elements were shown. If the element were present, then it will be represented with a different different colors. Now this iron with blue color, this oxygen with green color. Likewise, you can give different colors to indicate different elements presence. Okay. If in case if there is no green color shades were present for oxygen, it means that no oxide layers were formed. If it is formed, then obviously more amount of green colors were shown, then more amount of oxidation your implant material has undergone. Okay. So generally, if we are observing a small sample, okay, in SEM analysis, we could easily see what grain, each and everything that which we could easily observe. So now in generally, if you are observing any metallic sample, it will be having some kind of grains and grain boundaries. Okay, so which was shown in figure A and B. So this grain boundary is the one which is like very thick in nature. Okay, so generally where the corrosion it exactly happens. First, we should be knowing that. So the corrosion it generally happens only in the grain boundaries first of all. Then it will penetrate inside the grains. Then it will penetrate inside the subgrains. Okay, so the outer area which is called as a grain boundary, and inside that very big grain is there. Inside the grains, lot of millions of subgrains are there, which was shown in figure like 1, 2, and 3. We can see some kind of like inside a grain, many subgrains will be there. Okay, so right now I hope that you are aware that every grains are composed of a grain boundary. So the grain boundary only it will get corroded at first. Once the grain boundary is corroded, then automatically grains will get corroded, then subgrains will get corroded. Okay, so okay, it could be easily represented by means of this pomegranate. Okay, in pomegranate, just imagine that the outer area which is nothing but the grain boundary. Okay, so the outer skin which is called as the grain boundary. Inside the grain boundary, a bunch of pomegranates are there. So that could be called as a complete grain. So inside a pomegranate, millions of small particles, small granules are there, which could be called as subgrains. So first, the outer shell it will get corroded. Then the inner portion of the grain will get corroded. Then small subgrains will get corroded. So this is how exactly a grain boundary, a grain and a subgrain it exactly looks. So this pomegranate is one of the typical examples that which we could correlate with the metallography. Okay, so this corrosion it is a surface energy phenomenon. Okay, so wherever the surface energy is very high, then those areas will be like easily exposed to corrosion. For example, as I told you earlier, the grain boundary it is having the highest surface energy. Okay, so the outer area which is having the highest surface energy it will be like 600 millijoules per meter square. So the outer grain boundary will get corroded first. So we should be knowing what is our underlying scientific fact. Why grain boundary is corroded? Why not the grains or subgrains? Because the grain boundary it is having the highest surface energy. So the grain boundary will get corroded first, then grains will get corroded, then subgrains will get corroded. Okay, because the surface energy at the subgrains are very minimum, like 30 to 60 millijoules per meter square. So since it is having a very least surface energy, it will get corroded at last. So the grain boundary will get corroded at first. Okay. So it means that, like, if you are having a fine grain structure and a coarse grain structure, say for an example, if you are, I mean, if your material is in molten state, and if you are like cooling your material at a very high rapid rate, okay, so obviously if your metal is in red hot condition and when it is cooled very rapidly, then it will result in very fine grain morphology. Okay, so generally in mechanical perspective, fine grains are having very high, I mean, very high mechanical properties. Like it will be having very high tensile strength. It will be having micro hardness. It will be having a very high fatigue resistance. Okay, so fine grains are more preferable for most of applications. Okay, for mechanical applications. So if your material is like cooled in an open environment, for example, if your material is in red hot condition, you just left that material as it is in an open condition, then the material will cool down very slowly. Then automatically that will result in coarser grain formation. So once the coarser grains were formed, then those coarser grains doesn't have enough mechanical properties, because the coarser grain can easily, it will undergo fracture, but fine grains, it will never undergo fracture easily. Okay, so when you compare coarser grain structure and a finer grain structure is more preferable as compared to the coarser grain structure. But this from the perspective of corrosion resistance, these coarser grains are more preferable as compared to the finer grain structure. So that was the bottom line which I was mentioned over there. So coarser grains are preferable for highly corrosion resistant application. So based on the application only, we could tell that what type of grain morphology is necessary. If you want if mechanical property only, that is the most concerned requirement, then you could cool your material. When the material is in red hot condition, you could cool the material more rapidly so that you will be getting a fine grain structure, because you need mechanical property. Okay, so if you are like so concerned about corrosion resistance, then you have to cool down your material in a very slow rate so that your grains will go into a very bigger size. So obviously the material will be like more corrosion resistant, because every grains are composed of a grain boundary. So wherever small grains are there, small grains also, it will be having more amount of grain boundaries. Every grain is composed of a grain boundary. So we need we need a coarser grains for highly corrosion resistant application. Okay, if the mechanical requirement is there, then of course we can go for fine grain configuration. Okay. The grain orientation and texture phenomenon. Okay, let me tell you what is the grain orientation and texture. So grain orientation means, so in what direction the grains were grown. For example, if you are having a small plant, okay, now we just consider a plant and sunlight is over there at the top. So plant will grow, towards the sunlight direction, like opposite to the sunlight direction, the plant will try to grow. Okay, so likewise, each and every grains, okay, in a metal, that will try to grow in a direction wherever heat dissipation rate is very faster. For example, if the left side, if the heat dissipation is faster, then grains will try to go in this particular direction. If if the heat dissipation is more faster at the top, then the grains will try to grow perpendicularly straight. Okay, so it is like based on like what direction your heat dissipation is there. In that direction, your grains will try to grow in different directions. Okay, so in what direction each and every grains are growing. Okay, so that could be represented by means of inverse pole figure. Okay, so this inverse pole figure, it is a common technique which most of the research articles were emphasizing. So it could be generated by means of electron backscatter diffraction, EBSD analysis. Through EBSD analysis, you could generate this kind of like an inverse pole figure, which will be representing the different crystallographic orientations. Okay, so in what direction your grains were grown, that will be shown in terms of different color gradients. For example, if it is showing red color, so it means that in a particular direction your grains were grown. For example, if it is represented with the blue color, then your grains are grown like in a perpendicular some other direction. So each and every directions were represented with the different color gradients. So these maps could be generated by means of electron backscatter diffraction, so which is called as EBSD analysis. Okay, so using this inverse pole figure, you could say that in what direction your grains were oriented. Why I am particularly talking about this grain orientation means, not only the grain boundaries will determine your corrosion resistance. So this texture and this grain orientation, that will also one of the deciding factors for evaluating the surface energy. For example, for FCC material means face centered cubic material like stainless steel 316L or else this aluminium. Okay, many face centered cubic materials are there. So for such face centered cubic materials, this triple one direction, if the grains were grown, then obviously that will be having the highest corrosion resistance. Okay, as compared to the 100 direction, if a grains were grown, just imagine 100 means this direction, and triple one means this perpendicular direction, and 100 means this right side direction. Just you can imagine. So if there are three different directions, then the direction which is like more perpendicular, like which is triple one direction, which was represented with the blue color. So that particular material which will be having the highest corrosion resistance. So it is generally a well proven fact that for FCC material, triple one direction, it is having the least surface energy as compared to 100 direction and 110 direction. So obviously, triple one direction will be the highly corrosion resistant direction. If a material is having lot of blue colors, so it means that it will be like oriented. Most of the grains are oriented in triple one direction. So that that is more favorable. Okay, for example, if you are dealing with the HCP material, hexagonally closely packed material, magnesium, titanium. So the surface energy would be very less if it is oriented in 0001 direction. Okay, so if you are taking a EBSD graph, then you could generate this kind of pole figure. Through this pole figure, you could tell that either your material is corrosion resistant or not, because these are well proven facts. For FCC metal means tubular texture is more corrosion resistant. For HCP material like magnesium means 0001 basal texture is more corrosion resistant. So these based on this texture also, you could evaluate that what is the corrosion resistance of your material. So generally through potentiodynamic polarization itself, we could evaluate. But other than this, this EBSD kind of characterization, that will be like a corroborating evidence, like to support your claim. For example, if you are telling I have got so and so corrosion resistance, then you could add this kind of like EBSD inverse pole figure, and you could tell that most of the grains are oriented in triple one direction, and my material is FCC material. So obviously, it will be like more corrosion resistant, because it is already a well proven fact. They have proved with the different FCC materials and different HCP materials also that that was already evaluated, and they have found that the surface energy was very less only in certain textures. Okay, so we cannot abruptly tell that a coarser grain will be having a very high corrosion resistance and finer grain will be having a poor corrosion resistance. We cannot tell abruptly. So based on what texture it is oriented, in what direction the grains were oriented, based on that only we could come into a precise conclusion that either our material is going to be really corrosion resistant or not. So because everything was guided by surface energy only that determines what would be your corrosion rate. Okay, so least surface energy means the obviously the corrosion resistance is very higher. Okay, then let's move to the other slides as well. Okay, so I have addressed like what are the different types of corrosions were there. So in the implant material, pitting corrosion could happen, crevice corrosion could happen, fretting, galvanic and microbial induced corrosion could happen. So let me quickly rush into the previous slides and let me show that what is a pitting corrosion. So the pitting is the one which was shown in the okay, so which was shown here. So this type of corrosion is called pitting corrosion. Small holes would be formed. So this type of corrosion is called pitting corrosion. So it is generally due to the etching effect. 90% of all the implants, it will undergo pitting type of corrosion. Okay. So remaining 10% only, it could be of any other types. So 90%, most of the implants will undergo pitting corrosion. So you have to select a material in such a way that it should have a very high pitting corrosion resistance. Okay. Then the next one is the crevice corrosion. Okay. This crevice corrosion also it could be possible. Now, okay, so the crevice corrosion means it will come on the one metal to the other metal interface. Okay, so here you could observe some kind of crevice and fretting corrosion. Fretting corrosion means due to the rubbing effect, your surface will become like a lot of scratches and delamination. So in the delaminated surface, easily corrosion can happen. Okay, so now that kind of corrosion is called as fretting corrosion. For example, if you are having a metal, it will never generally get corroded. If we are taking a sandpaper and we are rubbing it and we are scratching the surface, then that scratched surface, it will undergo high corrosion, okay, like high susceptibility to corrosion. Okay, so that kind of corrosion, wear induced corrosion, is called as fretting type of corrosion, okay, which is nothing but wear induced corrosion. The other most common type is the microbial induced corrosion. Like this microbial induced corrosion means, for example, some small biofilms will get formed over the implant surface, and that biofilm, it will develop some lot of proteinaceous substance, and it will start corroding your implant. So that is called the microbial induced corrosion. Some bacteria will adhere over the implant surface, and it will cause some kind of corrosion effect, so which is called microbial induced corrosion. And galvanic corrosion is like more similar. For example, your nut is one material and your bolt is other material. Okay, for example, your nut is mild steel and your bolt is magnesium. When these two different materials are coupled together, then automatically some kind of galvanic reactions will be taking place, and at the mating interfaces between the bolt and the nut, some kind of corrosion will get happen in the presence of like water, like electrolyte, or in the presence of like moist environment. Some corrosion could happen. So that is called galvanic corrosion. When two different metals were coupled together, this kind of galvanic corrosions that could be possible. So mostly in prosthetics, if you are using a nut one material, then the same material only it should be used as a bolt material also. So if material, then galvanic corrosion could happen. For example, in a dental implant, the saliva will be acting like an electrolyte. If you are choosing one material like stainless steel, and the other material is another implant material is titanium, then when our saliva is there, these two material will interact with each other, and of course some kind of like galvanic reaction will be taking place. So because of this galvanic corrosion could take place. Okay, so here we could observe like the second most important factor is the surface morphology. Okay, the first factor is the corrosion resistance. Second factor, important factor is the surface morphology. Okay, so most of the bones are like very porous in nature. Okay, our bone, it will appear it is a calcinated bone, but however our bone, it will be having lot of micro porosities. If we cut our bone, then we could observe some small amount of like micro porosities. Okay, so generally, if we are producing an implant material, then it should be like biomimicking in nature. Biomimicking means it should replicate your human bone. Okay, because the bone is a very porous structure, and if implant is also like a little bit porous like this, then obviously it will support the osseointegration property. Osseointegration means bone joining ability. Okay, now here you could see some kind of like porous implant materials that are there, which will support the bone joining ability, because the bone is also very porous. Okay, so the bone, it will never consider this implant as a foreign body. Okay, because this implant, it is also having a lot of micro porosities, so it will enhance the bone joining ability. Okay, so even such kind of materials that was fabricated by additive manufacturing techniques. Okay, here you could observe how a human bone it generally looks. Okay, so generally a human bone, it will be having lot of micro porosities. Okay, so if you are like manufacturing a bolt without any micro porosities, then obviously the adhesion ability or the bone joining ability will be like very less as compared to the porous kind of implant. So this porous kind of implant are just a growing trend. Okay, so the surface morphology of the implant is very important. For example, as compared to the porous implant, the non-porous implant, it is having like less bone joining ability. Material is highly biocompatible material, even though both were manufactured with the same materials. But what is the surface roughness and what is the surface morphology? So based on that, the bone joining ability also will vary. Even though you may use the same material, but the bone joining ability that determined by the surface roughness phenomenon. Okay, so here like two bones were shown. Like one is the healthy bone, another one is osteoporosis bone, which at the old age, obviously the calcium will leach from the bone, so that will lead to osteoporosis. Okay, so that is one of the most common problems at the old age. Okay, so a lot of porosities will be there, so the bones will be like unhealthy. It will get broken. Okay, so generally when we should have a clear idea that bones are highly porous in nature. Bones are not completely a solid form. It is like having lot of micro porosities. Okay, so you have to produce an implant, even this kind of like biomimicking surface. So whatever the bone porosities are there, just like similarly you could produce an implant material accordingly. Okay. Then what are the different types of textures are available. Like if your implant is there, you could increase some kind of surface roughness. For example, like if your cycle tire, it has got punctured. Okay, what is the first step the mechanic will be doing is he'll be identifying the puncture spot, and he'll be rubbing that surface by means of emery paper, so that the glue will get fixed properly with the punctured zone. Okay, so they will be inducing kind of surface roughness because they will identify the spot, and after that they will be rubbing with the emery paper. Okay, so just like that, they will induce some surface roughness so that the adhesion ability will get improved. So likewise, this over the implant surfaces, you can see the surface roughness is a little bit higher. So small bone cells, it will get adhered with your bones. It will get adhered with the implant surface so that the bone joining ability will get enhanced more rapidly. So instead of a smooth surface in the second figure, you could see some small amount of surface roughness was there. That surface roughness will promote the bone joining ability of any implant. The osseointegration property of the implant would be enhanced based on the surface roughness and the surface morphology of the implant. Okay, so not only the material will be determining the compatibility and surface, biocompatibility and osseointegration property of implant. The surface roughness also plays a very vital role. And what type of surfaces are there? Either like a very rough surface are there, or else some features were given over the surfaces. That is very important. So generally, little bit like a rough surface will promote better cell adhesion. Okay, bone cells will get adhered more quickly. So which was shown in the first diagram. Okay, the third most important quality of material. You are choosing a biomaterial, obviously it will be like more biocompatible in nature. But however, how I could evaluate the biocompatibility of any implant material? So you could evaluate the biocompatibility by means of a testing, standard testing procedure, which is called MTT assay. Okay, so this MTT assay means, so it is a most common technique where we generally evaluate the biocompatibility of an implant. For example, like I have devised a very new implant. Okay, I have developed a new alloy. How would I know that either that alloy will be like having a very high biocompatibility or not? How I can assure that? Okay, the stainless steel, it is individually 316L, it is a highly biocompatible material, and titanium, it is a different material which is having a very high biocompatibility. And if I am mixing these two materials together to develop a new alloy, how could I assure that the new material will be more biocompatible? Individually, stainless steel is also biocompatible, titanium is also biocompatible. But how if these two materials were mixed to each other? Then maybe some kind of like intermetallic or some other new compound, it may affect or it might not affect the biocompatibility. So in order to clear that view, we can test our sample for MTTSA. We can cut a very small sample like 1 centimeter square, and we can dip our sample in the bone cells. Okay, like this MG63 bone cells, it is otherwise called as pre-osteoblast cells. Okay, so in that pre-osteoblast cells, you could immerse your implant over a period of time, like 5 days or 6 days. You can immerse, and you could see that how many bone cells are alive. Okay, for example, if your implant is having some kind of like a cytotoxic nature, like which is like toxic to the human cells, then obviously these bone cells, this MG63 type of bone cells, that will die, especially due to these toxic substances which are released from the implant. Okay, so generally biocompatible, and we could check the biocompatibility using this MTT assay. For doing MTT assay, we need human cells. So that human bone cells is nothing but the MG63 bone cells. So those bone cells, it could be procured from an open market, and it could be cultured in a small culture medium, and we could immerse our implant inside the culture medium for a duration like 4 to 5 days, and we could evaluate that how many cells are alive. Initially, how many cells were poured into the beaker, and after 5 days, how many are alive? Easily measure by means like optical density measurement. Okay, we could measure that how many cells are alive. Alive in it was shown. Okay, confocal microscopy, it is also one of the techniques where we could measure the cell viability. Okay, so either this MG63 bone cells we could use for evaluating the biocompatibility of the implant, or else if MG63 bone cells is not available, then what is the second option means we could go for L929 ortho cells. Okay, that we will be covering in the upcoming slides. Okay, so generally this Mg63 bone cells, it will appear in this form, like in optical micrograph. But if you are seeing this image in fluorescence microscopy, then it will be like represented with various color gradients like this. Okay, like different color gradients are shown. We will be using a red color stain. Okay, we'll be using red color stain to indicate the presence or absence of bacteria. Like if you are pouring the red color stain, that red color stain will be adhered over the bone cells, which could be easily identified, like either it is alive or dead. Okay. So only the alive cells, only these stains will be adhering. Over the dead cells, it won't be. There's a red color stain. It won't be adhered over the dead cells. So obviously, if it is like more black, it means that most of the cells were dead. If more amount of red colors were shown, it means that most of the cells were alive. So through this technique, we could evaluate what is the biocompatibility of your implant material. Okay, so if you are developing a new material, this is what the testing you are supposed to do. You have to do MTT assay, and now if you are interested, I will let you know where the facility. Okay, the next thing is like we can go for this fluorescence microscopy using a green or blue color stain. Different stains we can use to indicate the presence of bacteria. So in fluorescence microscopy, we could observe either the bone cells are alive or dead. Okay, so this is one of the most widely used techniques. Okay, so now if you are not having Mg63 bone cells, then you could go for L929 rat cells. Okay, so L929 cells are rat cells. So generally, before giving any implant to the human body, generally we used to check with the rat. Okay, so so if the rat is okay with that implant, then of course they will conduct the real-time testing with the human body. So now, if you are not having Mg63 bone cells, then you could evaluate your biocompatibility by L929 rat cells, which was like rat fibroblast cells, which was generally easily available in the market. Okay, this is how the cell structure it exactly looks. Okay, L929 cells. You could measure, you could immerse your implant inside that L929 ortho cells for a period of like 4 to 5 days, and you could evaluate how many rat cells are available. So if the most of the cells were dead, it means that your implant is cytotoxic in nature. Okay. So if most of the cells are alive, it means your material is biocompatible. Then the next one is the antibacterial ability. Biocompatibility, that is a different segment, and antibacterial ability is another phenomenon. Okay, your material can be biocompatible, but we cannot assure that biocompatible material is antibacterial in nature. It could be antibacterial, or it may not be antibacterial in nature. That we could determine only by antibacterial ability test. Okay, so generally in any implant material, the most common bacteria can adhere is E. coli bacteria, which is called the Escherichia coli bacteria. Okay, so this Escherichia coli bacteria, it can easily adhere over the implant surface, and it will cause some small biofilm. So those biofilms are very cytotoxic in nature. That will cause a lot of septic problems, like some fungus will attack over there, some kind of like formation here over the implant surface, and it will cause a lot of some septic shock as well. Okay, so generally your material should be biocompatible and also antibacterial in nature. For antibacterial in nature, generally we add cerium. Okay, cerium oxide, it is one of the most commonly used antibacterial materials. So those materials are coated over the implant surface, so that your implant material will be biocompatible as well as it is antibacterial in nature. Okay, so here they have cultivated that Escherichia coli bacteria, and they will fix an implant over that surface, and they will measure that either the bacteria is dying or not. If the bacteria were dead in the implant surface, it indicates that, then obviously your implant material is antibacterial in nature. Okay, so already it was proven it is biocompatible in nature. However, we should be aware that either the biocompatible material is antibacterial or not. Okay, to evaluate that, this E. coli bacteria was widely used. Okay, Escherichia coli. These are most common bacteria which will adhere over the implant surface within like 8 to 10 years. This kind of bacteria will slowly develop in the implant surface, and this bacteria will cause microbial induced corrosion. Okay, because the proteins which was synthesized by this bacteria, that will start etching your implant surface, that will drill your implant surface like this, and it will cause some lot of rust formation over the implant surface. Okay, so these E. coli bacteria now only we generally use, for testing the antibacterial ability of the implant. Okay, then the most common this E. coli bacteria which was cultivated over here, and it generally adheres over the surface and it will form a biofilm. So that was shown over here. Okay, so this is how the Escherichia coli bacteria it generally looks when it has formed a biofilm. So this is what a biofilm. When we observe in a microscopy, scanning ultra microscopy, or a confocal microscopy, we could see this kind of like a bacterial biofilm. Okay, that will be more visible. And these long bacteria are which is nothing but Escherichia coli bacteria. Okay. Here we could observe that initially one bacteria will get adhered over the implant, so one or two bacteria. So that bacteria will multiply, and it will form a very big bunch of bacterial colonies. Okay, so it will take a lot of time for making the, for the proliferation of this bacteria. So initially one or two bacteria will be there over the implant surface. Then eventually it will form a bacterial colony. Okay, so obviously your material it should be antibacterial in nature. So this is how a bacterial colony it exactly looks. Okay, in figure number D you could observe initially one or two bacteria were there in fig number A, and in fig number B it is keep on increasing, and figure D you can see a lot of bunch of bacteria were there, which is called as bacterial colonies. Okay, so it will get generally developed over the implant surface. So your implant surface should be antibacterial in nature. Okay, so that's the reason we are adding cerium. Cerium is a highly antibacterial material. Okay, coli bacteria, the Staphylococcus aureus. Okay, so that is also most common bacteria which will adhere over the implant surface. Okay, so that color graphs were shown in the left side. So that bacteria, and it will be like in a round spherical shape, but whereas E. coli bacteria like shape. Okay, so each and every bacteria that has its own structure. Okay, so what kind of biofilms are formed? If we want to confirm that, we could observe that in cell morphology. If it is like spherical in structure, then we could conclude that it is Staphylococcus aureus bacteria adhered to the implant surface. If it is shaped structure, then it means that E. coli bacteria was developed over the implant surface. So through the structure itself, we could conclusion that what type of bacteria was adhered over the implant surface. So if we are designing an implant material, our implant material should resist against this E. coli bacteria and Staphylococcus aureus bacteria. Okay? So it should have that antibacterial ability. Then the fifth one is nothing but the cell adhesion and the cell proliferation. Okay, so for example, our bone cells are there. Our bone cells will feel more comfortable to adhere over a porous implant as compared to a non-porous implant. For example, wherever the small microporosities are there, our human bone cells will feel more comfortable to adhere or anchor. Okay, just like a ship anchoring, it will try to anchor over the small porosity, and our bone cells will try to regenerate and it will start to grow. Okay, so the growing of more amount of our human cells. Okay, so which is called cell proliferation. Okay, that kind of cell proliferation that are possible over the porous implant. Porous implant are more biocompatible as compared to the non-porous implants. Okay, as I have told you earlier that this porous implant that mimics the human bone structure. So that is why it is having very good osseointegration property. So initially, if your surface is very glossy, so obviously the human cells cannot adhere properly with your implant surface. Okay, so if the implant is porous, then it could easily anchor your bone cells like MG63 bone cells or L929 ortho cells that could adhere over your implant surface, and it will enhance the bone joining ability in a very faster way. Okay. So I hope you would be aware like what is cell adhesion and what is cell proliferation. Cell adhesion means initially the cell will adhere, then later one cell will multiply into 1,000 cells, and it so that multiplication of proliferation. Okay, so generally we call it a cell proliferation. If bacteria is like multiplying more, we call it as like a bacterial replications. Okay, so this is how we generally denote. So your surface it determines like what would be the cell adhesion and what is the cell proliferation rate. That is dependent on your surface phenomena and the biocompatibility of your material. Okay, so if you are designing a material, then the surface should create a conducive environment for the cell initial adhesion and for the cell proliferation. Cells should multiply. Okay, one bone cell should multiply into 5 or 6 bone cells. Then only the cell adhesion will be like more better, and the osseointegration property will be more faster. Okay. So here in figure E and F, we could observe that cells were adhered at a very faster rate, and the cell adhesion is more in porous implant. Okay. Here, if the cells were proliferated, more amount of cells were formed, means then it will look this kind of like fibrous structure. So it means that more cells were grown, more tissues were grown, means that then it will appear in this way only. It is a stem morphology of a proliferated cells in the implant surface. In the implant surface, if cells and tissues were grown, then this is how it will generally look. It will take minimum like 5 to 6 months to form this kind of cell proliferation. Okay, so generally it will never happen as quick as possible. It will take its own ample of time. Okay, so here we could observe like a very good cell proliferation. So in day 2, day 4, day 6, this kind of cell proliferations were seen. But throughout the implant, the cell proliferation means it will take some time. Maybe in certain areas, the cell proliferation will be faster. Like within 6 days itself, you can attain this kind of cell proliferation. But throughout the implant means it will take some ample of time. Okay. So cell proliferation means the growth of human bone cells. So that is called cell proliferation. Okay, so here we have shown like how cells are adhered to the implant surface. It is completely based on the surface roughness. If your surface roughness is like a little bit higher, so the adhesion ability will be like much better. But rough surface will be always prone for corrosion attack, as we know already. So cell adhesion will be better, but but obviously the corrosion resistance will be poor. And not only the human bone cells can adhere over the rough surface, even a bacteria can also adhere over the rough surface. That is also one of the most common problems. So we could do this antibacterial assay. We could evaluate what is a bacterial adhesion ability over the implant, and what is the antibacterial ability over the implant, and how the bone cells can adhere over the implant through this fluorescence microscopy and confocal microscopy. We could evaluate all these phenomena. Okay. So, tribological resistance is nothing but the wear resistant implant. So here you could observe that this texture, it plays a vital role. Texture I have already shown like a inverse pole figure, like what is the direction of the cell growth. Okay, so that texture, it determines your tribological resistance. The sliding direction, like in what direction the sliding or rubbing is taking place, that is very, very important. And what is the grain morphology? Grain morphology in the sense fine grains are having high tribological resistance as compared to the coarser grain structure. So this grain morphology is very important. And what is the load that was applied during sliding? Like if you are applying a high load, then the friction will be more higher. Due to high coefficient of friction, your material will get worn out very quickly. Then the lubrication mechanism in the sense, some materials will be acting like a self lubricant. For example, if you are fixing an implant, then this blood, it consists of a lot of proteinaceous substances. That proteins will form a thin biofilm over the implant. That due to that protein adsorption, so your material will be acting like a self lubricant, which will be reducing the friction to a greater extent. Okay, so that lubrication ability also, that determines your tribological resistance. Then the compressive residual stresses, which we will cover in the upcoming slides, micro hardness and reinforcement addition also, that could be covered. Okay. So here the scratching resistance. Okay, the scratch test, if you are performing, what is the wear resistant of your material, that could be evaluated by scratch test performance. So this tribolone texture, okay, as I told you, tribolone texture is like highly corrosion resistant. The same tribolone texture is highly wear resistant. Tribolone texture is most important texture for FCC materials. Okay, so for FCC material like aluminium, stainless steel 316L, this tribolone texture, it is having the highest corrosion resistance and highest wear resistance. Okay, so we could observe how wear, I mean, it could be correlated with the grain orientation. Okay, if your grains are grown in this particular direction, if you are sliding in that particular direction, then your grains will delaminate very quickly. If you are sliding in a perpendicular direction to the grain growth, then then obviously the wear resistance will be higher. So the sliding direction, like one implant over the other implant, sliding direction is also very important. In what direction it is going to get slided, that will be a deciding phenomena of your wear resistant property. Tribological property is nothing but the wear resistant property. Okay. Then how a grain size that matters a lot in micro hardness. Okay, just we consider two samples, like both are magnesium only. So one is having a very fine grain structure, it means that it was cooled very rapidly. Another one was like a coarse grain structure. So this fine grain structure, like which was shown in figure B, it is having the highest micro hardness, which was shown in blue color diagram in figure 4. Okay, in figure 4 you can see the peak value, like what is the micro hardness value of a magnesium implant. So that second one, that V1 was represented with the blue color diagram, micro hardness graph, which was shown in figure 4. Okay, so it is having fine grains generally have higher micro hardness, coarse grains generally have poor micro hardness. So it is based on Hall-Page empirical relationship. So based on the Hall-Page empirical relationship, always a finer grain will have better micro hardness, and if the micro hardness is very high, then the material will be having high wear resistant properties. Okay, so obviously fine grains are more preferable for wear resistant application. If you are not concerned about wear, if you are concerned only about the corrosion resistant property, then coarser grains are preferable, and that too preferred a triple orientation. Okay, especially for FCC metal. For FCC metal only triple orientation, that is giving the best results. But for HCP metal, 0001 orientation of grain growth is more preferable. So compressive residual stresses. So I have given a foundry as an example. So whenever your material is got, and if you are giving a hammer blow, then more amount of stress will be accumulated, more amount of compressive stress will be accumulated in your material, and that material will turn like a very high strength material, and that material can resist against corrosion and also wear. Okay, so that is the most important one with the effect of compressive residual stresses. So implant is there, it should have very high compressive residual stresses, so that the wear resistance also should get should be it would be more higher, and also the corrosion resistance also would be more higher if the compressive residual stresses are more high. Compressive residual stresses, it could be induced through this kind of hammer blows, or else like a lot of techniques are there, like hot isostatic pressing. So that is also one of the most common techniques. So through that we could increase compressive residual stresses, or else we could do some kind of ultrasonic cleaning. Cleaning means a small hammer will be there, it will be like hitting your implant surface in ultrasonic with the ultrasonic vibration. So due to that, automatically the micro hardness of the component will get enhanced, which will result in high wear resistant property. Okay, and another thing is like tribofilm chemistry. Okay, tribofilm chemistry in the sense I have already told. Whenever the material is corroded or if it has undergone some wear, it will lose a lot of free electrons. While losing lot of free electrons, then automatically some kind of like oxide layer will get formed. So those oxide layers could be easily captured by means of this XPS spectrum. It's like a X-ray photon spectroscopy. Okay, so X-ray photon spectroscopy, it is the most common technique to evaluate what type of oxide layers were formed. Either the oxide layer can be chromium oxide or iron oxide or molybdenum oxide or any type of oxide materials could happen. So what exactly the oxide layer was formed? So either it is molybdenum oxide, means exactly molybdenum, or chromium oxide, or what exact type of oxide layer was formed. So in order to identify that, we generally go for XPS spectra. Generally we could see that some rust has happened. That rust, what material it was made of, we are not aware. To know what type of rust it has formed, either chromium oxide rust or iron oxide rust, or else either nickel oxide rust was formed. So in order to identify that, we generally go for this tribofilm chemistry analysis by means of XPS spectra. So here you can see that before corrosion, you can see what is the XPS. After corrosion, you can see after once the oxidation has taken place, you can see some iron oxides are formed. Okay, Fe3 plus means iron oxide, like a Cr2O3, this chromium oxide. MO6 plus is like molybdenum oxide. Okay, so this kind of like different oxide layers has been formed. So you could observe all these things through XPS spectra. Okay, so that is also one of the most common technique. most common techniques which was employed in biomedical industry. Okay. Here I have shown this titanium implant as an example. So for corrosion, this titanium, pure titanium was not oxidized, but after corrosion, you can see that titanium was converted into TiO2 passive film. Okay, so it means that your titanium got corroded. TiO2 passive film also that was formed. You can see exactly what passive film is formed. Titanium oxide, it could exist in TiO or TiO2 or Ta2O3. It can exist in many forms. Exactly what form it was existed. Okay, so you could observe that through XPS spectroscopy. Okay, and I have shown the corroded morphology in the left hand side. You can see. Okay, then the last one is like cytotoxicity testing. Cytotoxicity testing in the sense like either what type are, I mean, during the time of corrosion, what are the different materials or different ions like releasing. Okay, so that is very, very important. As I told you that this nickel will be causing a lot of allergic reactions in our human body. This nickel allergy will lead to like a lot of rashes and kind of septic shock. So nickel is the most concerned one, and titanium, if small titanium are released, especially during the time of corrosion, then that will also damage our body. It will increase oxidative stress levels in our body. So how I can find what are the elements are released, especially during the time of corrosion. For that, we need two equipments. So one equipment is like inductively coupled plasma optical emission spectroscopy (ICP). Through this technique, we could detect either the titanium or molybdenum is released in the simulated body fluid environment. We could observe that through this inductively coupled plasma optical emission spectroscopy. Using that, we could observe that how much quantity of titanium was released, how much quantity of molybdenum was released, okay, in what weight percentage it was released. Okay, so there are some certain criteria that maximum in one day, like 10 milligram per liter of titanium only it should get released. Okay, so if the titanium was released much more than 10 milliliter per day, then obviously a lot of cytotoxic, like it will be toxic to the human cells. So during the time of degradation, so what type of materials are getting released during corrosion? So and when what weight percentages it was being released. So we can analyze that through these two equipments. One is inductively coupled plasma optical emission spectrometer, and also there's electrothermal atomic absorption spectrometry. Through these two techniques, we could observe that what are the various type of material that was released during the time of corrosion, because these elements that will mix with blood of allergic reactions. So we could identify those things through these two techniques. Okay, so if you are interested, I will let you know where these facilities are available. Okay, then the last one I would like to cover is the stem cell regeneration therapy. Many people would not be aware about this technique. For example, if your tissue cells were dead, say for an example, if some patient is having some kind of cardiac, like cardiac arrest, and if the cardiac muscles was it was completely, it has become dead. Okay, then you could inject some quantity of stem cells. Okay, stem cells. It is present in the bone marrow. The stem cells that are present in the umbilical cord of the baby. Okay, so especially when during pregnancy, he is like coming out, then the umbilical cord of the baby, it will be having very rich stem cells, and that stem cells, it could be preserved in a cryogenic temperature like -23 or -24. Likewise, in a very high cryogenic temperature, it could be preserved, and stem cells could be extracted from that. And whenever that baby is having cancer in future, using that stem cells, we can cure that dead tissues. Okay, we can regenerate that dead tissues using the stem cells. Okay, so if you have cells, then it could be used for hard tissue regeneration also. That could be possible. Even a dead tissue, which was shown on the figure number A, those kind of dead tissues, it will start regrowing. So instead of replacing a normal heart with some other heart, so this kind of tissue regeneration technique is more viable at present. So of course, you people should be knowing this. So that's why I have shown this kind of figure. Then the same stem cells, it could be used for tooth implantation as well. Okay, for example, if your teeth has undergone some kind of caries, which is called a tooth decay. Then you can drill that decayed area, and in that you can fix some small stem cells inside that area. Then automatically the teeth will start regenerating. Okay, instead of removing a teeth and instead of fixing a new one, you could regenerate your natural teeth. Okay, so this stem cells also, it is like fast growing technique at present. So when we are talking about materials, so this kind of like stem cell regeneration therapy also should be given complete importance. Okay, so with this, let me end this session. Thank you. If you have any queries, you can please go ahead. Hello.
Sir, Chakravarti sir.
Yeah. My session is over, and right now it is open for queries. Yeah.
Okay, sir. If any biomaterials applied in automobile engineering, sir.
Biomaterials applied in automotive application means you can. Okay, so this titanium 6Al, like 6%, 4%. That alloy was commonly used in aeronautical application. Okay, so the same, it is a biocompatible material, and the same material that was used as an implant material as well. Okay, so you can use the same material for implant, also for automotive application also you can use. Yeah.
Okay, sir. Thank you, sir.
So if you have any queries, you can please go ahead.
Okay, sir. Arun, sir. Arun?
Sir, yes, sir.
Sir, if there is any questions from audience?
Yes, sir. I just asked him. Mr. If you have any doubts, you can. Mr. S.M. Muzaki.
Be open, like whatever the doubts, it may be trivial or whatever. If you are having any doubts, you can please feel asked.
Okay, sir. No problem, sir. Thank you for giving a wonderful lecture, sir. For past couple of hours regarding the biomaterials, sir.
Okay, fine then. Yeah.
I will circulate your email ID and your other details to our students, and they will be asked to in personal, sir.
Yeah, fine then. Yeah. Okay, thank you.
Thank you, sir. Arun? Arun, thank you.
Thank you.
Thank you, sir. Thank you, Chakravarti, sir.
Yeah.
Thank you so much, sir.
Yeah, thank you. Okay, fine. Thank you.
I just end the meeting. Thank you.
So shall I end this session? Yeah.